Today, we are undertaking a truly radical journey. We're going deep into the future of computation.
But we're doing it by looking back.
Exactly. We're looking back at the most fundamental, inescapable laws of the universe, the laws of thermodynamics.
And this could really be a pivot point. We're talking about a proposed paradigm shift away from the deterministic brute force engineering of classical computers.
The ones that we all have on our desks and in our pockets.
Right. And those computers fundamentally spend massive amounts of energy actively fighting the noise of nature. The new approach, the radical one we're diving into today, it seeks to, well, control and harness the inherent randomness and thermal noise of the physical world.
All to accelerate AI.
All to accelerate AI.
And the figure leading this charge is just fascinating. Guillaume Verdon, he's a Canadian mathematical physicist, was a key contributor at Google on their quantum machine learning efforts, and now he's the co-founder of Extropic AI.
But that's only half the story, isn't it?
Not even. Because you might know him better by his highly visible alter ego, Bass Biff Bezos.
A character in his own right.
Absolutely. And this is key. He's not just trying to engineer a faster chip. He is attempting to accelerate humanity itself through this technology. It's all wrapped up in this philosophy that argues that stagnation isn't just, bad policy, but a violation of physics.
So our mission today has to be comprehensive. We need to unpack the entire stack here, from the philosophy down to the hardware.
Where do we start?
We have to start with the foundational physics. We need to analyze why modern chips are hitting this hard power limit, this problem of what's called excess entropy production. Then, from there, we can explore the vision of thermodynamic computing.
And look at the actual hardware.
The concrete hardware being built by Extropic and others, these thermodynamic sampling units, or TSUs. And finally, we have to critically examine the claims, which are immense, the ideology behind it, and of course the risks that come with trying to merge fundamental physics with radical accelerationism.
Okay, let's unpack this, starting with the core urgent problem, the power wall. For the last, 50 years? We've relied on Moore's law to just give us more computing power.
It was a given.
It was a given. But right now, we are hitting severe physical limits. So why are our classical CPUs or GPUs or TPUs, the entire backbone of modern AI, why are they fundamentally running out of road?
It's purely a problem of physics. I mean, it comes down to energy and heat dissipation. When we talk about AI today, we are talking about training these massive models.
The energy investment is just astronomical.
It's astronomical. And the issue is that conventional chips are reaching physical limits on speed. If you look at any high-end microprocessor, their clock cycles, they just can't reliably exceed, say, 5 to 6 gigahertz.
And that's not because we don't know how to wire the circuits to go faster, right? It's a heat problem.
It's entirely a heat problem. The moment you try to push those clock cycles higher, the rate of heat accumulation inside that tiny silicon structure, it just outpaces the rate at which you can effectively pull that heat away.
You get thermal runaway.
You get thermal runaway. It's a cooling and heat transfer problem, but at the scale of nanometers. We are spending truly extraordinary amounts of money on increasingly elaborate, power-hungry cooling systems just to keep the chip from literally melting itself.
So we're stuck in this vicious cycle. We need more computation for better AI, but that computation generates heat, which limits the speed.
Which then forces us to build bigger and bigger, more centralized data centers that need even more power and more cooling.
And that just makes the whole initial energy problem even worse.
Absolutely. And this is the core argument that's driving this whole thermodynamic computing movement. And it's something Verdon articulates very clearly. Solving this with brute force energy generation is just too slow.
You can't just build more power plants.
Well, you can, but yes, you need to increase global energy production long term. They even talk about, eventually reaching for a theoretical Dyson sphere, but that's decades, if not centuries away. The immediate crucial problem is improving computer efficiency right now.
Because AI scaling is bottlenecked.
It's bottlenecked by thermal energy dissipation. The most efficient lever we have isn't a bigger power plant. It's fundamentally better physics at the chip level.
We can try to move mountains, or we can look for a much, much more efficient shovel.
That's a perfect analogy.
And to understand why classical computing is such an inefficient shovel, we have to go back to the fundamental link between thermodynamics and information.
To really grasp the inefficiency, you're right, we have to start with the foundational physics of computation. And this is a line of inquiry that is well over a century old. We have to begin with Landauer's principle.
This isn't just some modern computing theory, is it? This goes all the way back to the historical discussions around heat engines and information. I'm thinking of Maxwell's demon in the 19th century.
You're exactly right. Maxwell proposed this thought experiment, right? A tiny, intelligent demon that could sit at a gate between two chambers of gas and sort molecules. It would let hot molecules go one way and cold ones the other.
And that would seem to violate the second law of thermodynamics. You'd be creating order from chaos for free.
Exactly. And this paradox, it tormented physicists for decades. It was Rolf Landauer in 1961 who finally resolved it by making the crucial link between information and energy. He argued that the act of gaining information, or more accurately, the act of erasing information, is a physically irreversible process.
And what does Landauer's principle state specifically about that process?
It states that any logically irreversible process, so for example, taking two possible states, like a 0 and a 1, and merging them down to a single known state, say a 0, that process must be accompanied by entropy production.
And that entropy production shows up as heat.
It manifests as heat dissipated into the environment. The absolute minimal heat dissipated for erasing a single bit of information is now known as the Landauer bound, or LB.
So the Landauer bound is the theoretical absolute minimum energy cost. It's the toll the universe demands every single time we wipe a memory slate clean.
It is.
But, and this is the critical point, modern computers don't even get close to that minimum, do they?
Oh, not even close. They're not in the same ballpark. Classical computers today dissipate many, many orders of magnitude more heat than the Landauer bound requires.
So where is all that extra heat coming from?
Well, Landauer's early work was essential, but it had its limits. It had to rely on what's called equilibrium statistical physics, which restricted his analysis to these, simple, reversible processes near ideal conditions.
But a working computer isn't an equilibrium. A CPU running a complex program is a dynamic, messy system.
It is fundamentally an out-of-equilibrium system, and that distinction, equilibrium versus non-equilibrium, is where the real revolution in this field happens.
This is where things get interesting.
Absolutely. The breakthroughs in non-equilibrium statistical physics over the last couple of decades gave rise to this whole new field called stochastic thermodynamics of computation. This is the toolbox that companies like Extropic and normal computing are using.
So what does this new toolbox let us do?
This new framework lets physicists calculate the energetic costs for complex real-world systems. Things like Turing machines, digital circuits, even biological automata, which all operate far, far from equilibrium. This is really the first time we can truly combine computer science theory with non-equilibrium stochastic thermodynamics at a foundational level.
Okay, so let's use this new framework to calculate all that wasted energy, the cost of fighting thermal noise. This is what you call the excess entropy production, or EP. How is the total cost of a computation broken down?
The total energetic cost, which we can call the effective free energy, or EF, is a very precise sum of two terms. The first term is that minimal cost we talked about, the Landauer cost, LP. That's the energy change required by the laws of information physics.
The unavoidable universal tax.
The unavoidable tax. The second term is the problem child. It's the excess entropy production, sigma of P, or EP.
So the total energy is the necessary cost plus all this wasteful inefficiency. The EF equals L of P plus sigma of P.
That's the perfect way to frame it. And the sources we're looking at, they go even further. They provide a crucial decomposition of that wasted term, the EP.
It can be broken down even more.
Yes. The excess entropy production can be broken down into two non-negative functions. And non-negative is key, meaning they can only ever add to the waste. They can never reduce it.
Okay, walk us through those two components of waste.
The first component is the mismatch cost. This reflects how far the initial state of the system is from an optimal stationary state for the calculation you're about to do.
Give me an analogy for that.
Think of it this way. When your CPU starts a task, if the initial configuration of all its little circuit elements is thermodynamically far from the optimal state for that specific calculation, you immediately waste energy just getting it into the right starting zone. It's like firing a cannon when the powder is damp. You waste a bunch of energy just heating it up before the launch even begins.
I like that. So the mismatch cost is the wasted starting energy required because the hardware wasn't thermodynamically prepared for the job at hand. What's the second component?
That's the residual EP. And this reflects the remaining inefficiency that's just inherent in the physical process itself. It's like the friction during the run. Even if you started in a perfect optimal state, the actual physical steps, the switching of gates, the movement of charge, They are not perfectly reversible. So you generate heat loss due to friction and other microscopic irreversibilities as the computation proceeds.
So here's the key takeaway, and I think this is what these new thermodynamic chips are built to exploit. Why does the very structure of a modern digital computer guarantee that it is constantly wasting energy this way, constantly incurring this excess entropy production?
It's the clock.
The clock cycle.
The clock. Modern digital computers are synchronous devices. They are governed by a constant, rigid clock cycle. They repeat the exact same underlying physical process over and over again, a fixed, irreversible sequence of logic gates on it, a system that is almost always not at its thermodynamic stationary state for every single calculation.
So the very thing that makes them predictable, the synchronization, is the enemy of thermodynamic efficiency.
It is the enemy. The moment you force a physical system to repeat a fixed, irreversible process on an initial state that isn't the optimal steady state, it will generate positive EP. With every single clock tick, they are constantly paying the mismatch cost and the residual EP tax because they can't dynamically optimize their state for every calculation.
Classical hardware is designed for predictability, but that predictability is what ensures thermodynamic waste.
And thermodynamic computing aims to abandon that synchronous clock entirely. It wants to let the physical system dynamically find its own optimal lowest energy state for a given problem.
That fundamentally reframes the cost of computing. It's not just about the bits anymore. It's about the underlying physical mechanism of switching. Now, something else came up in the research that seems counterintuitive: topology, the physical layout of a circuit. How can the wiring diagram affect thermodynamic costs? Isn't information theory separate from architecture?
In an abstract sense, maybe, but not when you're considering real-world physics, the connectivity or the topology of a circuit. And this applies to a CPU or even, gene regulatory networks in a cell. It physically restricts which variables can couple or interact with each other.
And that restriction has energy consequences.
It fundamentally affects the available pathways for energy dissipation. This is a thermodynamic constraint.
This leads to this concept I read about, Landauer loss.
Yes, Landauer loss, or L loss. It's a concept that comes directly out of stochastic thermodynamics. It measures the difference in entropy costs you observe when you only look at a small part of the system, a subsystem, versus measuring the entropy change of the entire interconnected system.
So if I only look at one wire, I might calculate one cost. But if I zoom out and see the whole circuit, the global cost might be different.
Exactly, because the circuit topology physically couples all the processes, and that coupling itself is a thermodynamic constraint that changes the energy landscape.
Okay, but here's the part that I need you to clarify. The research suggests that in some highly constrained systems, the overall circuit might incur less total waste than an unconstrained process. How can a restriction, a constraint, lead to less waste? That feels like it's breaking a rule.
It's not magic, but it is subtle. Think of a circuit's topology as forcing energy to flow down specific channels. In some cases, the restrictive wiring diagram can actually prevent the system from wandering into inefficient high-energy pathways it might otherwise explore if it were unconstrained.
So it's like putting guardrails on a highway. It restricts your freedom, but it prevents you from driving into a ditch.
That's a fantastic analogy. It means the sum of these different loss terms can, in certain circumstances, be negative. This negative value reflects that the constraint itself imposes a physical regulation that guides the system toward more efficient states compared to a theoretical equivalent unconstrained process.
So the key insight here is that topology isn't just an engineering problem of cramming more transistors onto a chip. It is a critical thermodynamic factor.
Designing the physical layout is equivalent to designing the most efficient energetic pathway for the computation. And this is where the engineering of these new thermodynamic chips really starts, with the physics of the layout.
Okay, so if classical computing is stuck fighting this power wall, paying this massive excess entropy production tax,
then the vision of thermodynamic computing, or TC, is a complete paradigm reversal.
instead of forcing deterministic high-precision math and actively spending energy to suppress thermal noise,
TC proposes to control and harness that noise.
the computation is no longer a rigid step-by-step assembly line.
Exactly. It's viewed as an engineered, multi-scale, complex physical system. And when you expose it to inputs, it spontaneously transitions between states and refines its own organization, naturally driven by the laws of thermodynamics towards a solution. This is the heart of what's called stochastic computing.
We stop fighting nature and we start using nature's own processes to do our calculations. Why is this suddenly the perfect time for this kind of transition?
It's because the nature of the problems we're trying to solve with AI has fundamentally changed. A decade ago, the focus was on, say, deterministic classification. Is this a cat or a dog?
Right. A clear, single answer.
A single answer. Today, the focus is on generative AI. We're talking large language models, diffusion models, energy-based models, and these models are inherently probabilistic. They operate by sampling from incredibly complex probability distributions. A diffusion model, for instance, is literally a simulation of a noisy physical system being reversed.
And it is profoundly inefficient for our deterministic classical hardware to run these probabilistic tasks. We waste energy enforcing determinism, and then we waste more energy using algorithms to generate pseudo-random numbers to simulate the very randomness we just spent a fortune suppressing.
That is the ultimate inefficiency paradox of modern AI hardware. You're using a high-precision, multi-million transistor calculator to perform what is essentially a highly efficient coin flip simulation.
So TC just cuts that out completely.
It cuts it out. It replaces the rigid deterministic bit with the p bit, the probabilistic bit.
The p-bit. So how does this basic unit differ from, say, a quantum qubit or a classical bit?
Well, a classical bit is a guaranteed 0 or a guaranteed 1, stable. A p-bit, at any given moment, physically flickers between 0 and 1 with a certain probability, p.
And what drives that flickering?
Thermal fluctuations, the very noise that classical chips try to eliminate. And when you build a network of these p-bits, the interactions among them, as they're all coupled together, they naturally implement the target probability distributions you need for these AI tasks. Extropic calls this network a thermodynamic intelligence substrate.
So instead of calculating a solution step by step, the physical system just settles into a state that represents the probabilistic solution.
Yeah.
And it uses minimal energy because it's a natural physical process.
Exactly. And this is where Extropic claims they can slash the energy per sample by orders of magnitude.
Let's put that claim into context. What does orders of magnitude really mean here?
Okay, so if a current top-tier GPU takes, say, 100 watts to generate a high-quality sample from a distribution like generating a paragraph of text or part of an image, Extropic is talking about reaching that same quality sample using maybe a few hundred milliwatts, or even microwatts.
So that's a potential 100x or even 1000x efficiency gain per computation.
That's the claim. And that is the kind of leap you need to circumvent the power wall and extend the scaling of AI far beyond what we currently think is achievable.
Now, we have to address the elephant in the room here. This sounds extremely close to quantum computing, which also relies on probabilistic states.
It does.
And Guillaume Verdon, the founder of Extropic, he came directly from Google's quantum machine learning division. So why the pivot? Why not just stick with quantum?
I think this reflects a point of disillusionment that many in the quantum field are now facing. Verdon realized that while quantum machine learning offered these powerful conceptual advantages, the engineering challenges of building a fault-tolerant quantum computer, specifically the battle against noise, are just immense.
It's run a very long timeline.
A very long timeline. Comparable to developing viable nuclear fusion, it's a grand challenge problem.
What are the specific thermodynamic penalties of quantum computing that they're trying to avoid?
The primary penalty is noise mitigation. To maintain that fragile quantum state, what's called coherence quantum computers need to be at near zero temperatures. We're talking below 10 millikelvin.
Which requires massive refrigerators.
Massive, energy-intensive cryogenic refrigeration systems. And on top of that, you need quantum error correction, which is an incredibly complex and power-hungry process required just to keep the qubits stable and free from errors.
So in the thermodynamic terms we were just using, quantum error correction is essentially a high-powered, localized refrigeration unit whose only job is to pump entropy out of that delicate quantum core.
That's exactly what it is. It's an active, energetic, and very expensive battle against the environment. Verdon and the other TC proponents, they realized they could take inspiration from quantum engineering building blocks. These devices that already incorporate non-classical physics, but operate them in a higher temperature thermodynamic regime without needing quantum coherence.
They don't need the system to be perfectly isolated from the environment.
No, they need to control the environment's noise, not eliminate it.
And that makes the technology inherently more practical and scalable, doesn't it?
That's the hope. The goal is room temperature, large-scale manufacturability using standard semiconductor techniques, or at least techniques far less exotic than superconducting qubits. They're moving from the very cold to the thermodynamically savvy.
The goal is to leverage principles similar to what nature uses, but build devices that are ultimately better.
Better than nature. more efficient.
Okay, let's delve deeper into the figure driving this revolution. Guillaume Verdon. He's clearly operating on two levels here.
Yeah.
You have the mathematical physicist, and then you have Bezos, the viral figurehead.
This dual identity, it's a very conscious strategy. Verdon is the CEO, he's the technical bridge to academia, he's securing the patents, the investment. Bezos is the co-founder of the Effective Accelerationism Movement, or EDA.
And that alter ego functions as a viral intellectual provocateur.
A hype man, or intellectual Hulk, as he's sometimes described. The idea is that this persona is necessary to achieve unreal levels of excitement and to maintain the cultural momentum for invention in a world that Verdon believes is otherwise prone to stagnation and pessimism.
So this means the technology is fundamentally wrapped up in an ideology. What exactly is effective accelerationism, and how does it connect to these highly efficient chips?
EAC, at its core, is a philosophy of radical viral optimism and growth. It holds that the default state of the universe is entropy, it's disorder. And the purpose of life, of civilization, is to counteract that by maximizing technological growth and complexity.
Stagnation is seen as a physical failure, not just a societal one.
Exactly. They believe civilization must scale up by aligning itself with what they see as a natural principle of maximal growth.
So the connection to the chips is very direct. If the scaling of AI is currently blocked by a physical barrier, the power wall, then breaking that barrier is the most effective way to accelerate civilization itself.
Precisely. And a key tenet of AI is maintaining variance and competition in the system, in the marketplace, in ideas, in code. The goal is to ensure the overall system remains adaptive and fault-tolerant. This is the ideological application of the physical concept of robust, delocalized systems.
So let's talk about the company itself. Extropic AI, founded in 2022. Their core product is the Thermodynamic Sampling Unit, or TSU.
And that name, the choice of words, is deliberate, and it's critical for differentiating them from standard hardware. They explicitly call it a sampling unit.
Not a processing unit.
Not a processing unit. The core function is not to deterministically calculate that 2 + 2 = 4. It is to produce high-quality, high-speed samples from a complex, programmable probability distribution.
And the ultimate pitch, which is what drew in the $14.1 million in venture capital, is that massive efficiency leap.
Yes, they pitch the TSU as the solution to the energy crisis in AI. They're promising to slash energy per sample by orders of magnitude, those 100x to 1000x efficiency claims we mentioned, and effectively extend the trajectory of compute scaling far beyond the limits imposed by classical silicon.
Okay, let's shift to the critique. Because when you promise 1000x efficiency and you combine that with the persona of Bezos, the scrutiny is going to be intense.
Absolutely.
They raised the money, but the skepticism is massive, particularly because they missed their target alpha launch date, and as of late 2025, there were no verifiable public papers or patents.
And that is the core of the risk assessment. The bear case here argues that these grand claims are outstripping the actual science. Missed deadlines, they just fuel the critics who are asking, is thermodynamic computing just a classical stochastic computer that's been rebranded with a bunch of theoretical buzzwords?
The proprietary nature of it doesn't help.
No, the fact that the technology is shrouded in this early stage secrecy, it just exacerbates that fear.
So as an informed listener, how do we distinguish this physics-based vision from just, classic Silicon Valley vaporware hype?
I think we have to look at their approach versus traditional hardware development. Their counterpoint to all the skepticism is that they're not just incrementally improving transistors, and they're not just mimicking brain architecture like some neuromorphic devices try to do.
They're starting from first principles.
That's what they emphasize. Extropic is bridging the entire technological stack. They are simultaneously engineering the hardware and the algorithms based on thermodynamics and information theory all at the same time.
The idea being that you can't truly optimize the system unless you design the physical device and the software that runs on it together, grounded in the same set of physical laws.
Exactly. They are confident that their local neighborhood of ideas, this convergence of physics, thermodynamics, and AI models, is the necessary path forward. They claim that only by hacking physics directly can they achieve this level of efficiency, rather than just waiting for marginal gains from the existing silicon roadmaps.
They're betting the farm.
They are betting that the foundational physics theory is so sound that the engineering payoff is inevitable, even if it's delayed.
Okay, we have the theory, the land-hour cost, and the excess entropy production, and we have the high-level vision from Extropic. To ground this in reality, though, We need to look at tangible hardware that has demonstrated verifiable results and actually published its work.
And this brings us to normal computing and their stochastic processing unit, or SPU.
Normal computing is a critical reference point here.
It is, because their work is characterized by transparency and published papers. It allows us to see a concrete implementation of these ideas. The SPU is a functional, continuous, variable thermodynamic computer.
Meaning the variables are continuous, like a voltage, not discrete, like a digital 0 or 1.
Correct.
And what are these devices physically built from? Are they exotic?
Not really. They're built from standard RLC circuits, resistor, inductor, capacitor circuits constructed on a normal printed circuit board. The key insight is that the resistor component is the engine of thermal noise.
The part that classical computing sees as an error source.
Exactly. In the SPU, that resistor is the source of the necessary thermal fluctuations. The inductor and capacitor components then define the potential energy landscape that the system naturally settles into.
They demonstrated an initial version with 8 coupled unit cells.
Yeah.
What are the 2 main computational tasks this SPU can perform natively using physics?
The 2 main primitives they demonstrated were, first, high-speed sampling from complex distributions, and second, efficient linear algebra operations.
And both of those are essential bottlenecks in modern AI.
Huge bottlenecks.
Okay, let's focus on sampling first. Generative AI relies heavily on sampling from, say, a Gaussian distribution. How does the SPU use thermal equilibrium to do that efficiently?
It relies on the elegance of statistical mechanics. If you design the potential energy function of that SPU circuit to be quadratic, which is actually simple to do with standard components, then at thermal equilibrium, the dynamical variables in the system, specifically the voltages across the capacitors, they will naturally follow a Boltzmann distribution.
And for a quadratic potential, the Boltzmann distribution simplifies perfectly to a Gaussian distribution.
A Gaussian distribution. The physical system, simply by reaching thermal equilibrium, is mathematically performing the sampling. You don't program a pseudo-random number generator, you just let the voltages fluctuate due to thermal noise until they settle into the distribution that's defined by the circuit's connectivity.
This is critical for diffusion models and other types of generative AI that literally mimic noisy physical processes. The SPU is running the noise natively.
Yes. They successfully demonstrated Gaussian sampling. But, there are practical challenges, what are called sampling fidelity challenges, which highlight the trade-offs of using these physical processes.
You can't just measure the state instantly, can you?
Exactly. If you sample too quickly, the system hasn't fully decorrelated from its previous state. The output samples become time-correlated, which decreases the fidelity. They aren't truly independent samples from the distribution anymore.
So what do you have to do?
The research shows you have to wait. You have to wait for the system to thermalize and fully decorrelate. They found that waiting for an interval of at least 5 times the system's correlation time, what they call 5 tau core, is necessary to ensure high-fidelity, decorrelated samples.
And that correlation time, tau core, is a physical property of the RLC circuit itself. It's determined by the values of the components.
Right.
So the maximum speed of the computation is physically dictated by how fast the system can naturally shake off its memory of its previous state.
Precisely. It's an efficiency trade-off dictated by physics, not by clock speed engineering. You save a massive amount of energy, but the speed of your sampling is bounded by the system's thermal dynamics.
Okay, so beyond sampling, normal computing pushed this further. They went into core algorithmic tasks that are traditionally dominated by classical digital hardware. This is where the linear algebra experiment comes in.
And this was a major demonstration. This was the first thermodynamic linear algebra experiment, specifically doing matrix inversion. This is a big deal because it proves TC isn't just for some esoteric AI sampling. It can attack core numerical bottlenecks.
Why is matrix inversion so famously difficult and so important?
It is the dominant computational step in countless scientific and AI algorithms. A great example is Gaussian process regression, or GPR. The problem is that the algorithmic complexity of matrix inversion scales at O(n) cubed.
So as the size of your input matrix n doubles, the computational time increases by a factor of 8.
A factor of 8. This n-cubed scaling factor is a severe bottleneck in modern computing. It's why we have those centralized, massive data centers we discussed earlier.
So how did the SPU bypass that algorithmic complexity?
By using physics. Instead of running a complex digital algorithm that takes O(n)³ steps to calculate the inverse of a matrix, the SPU is engineered so that the physical system's equilibrium state is the solution to the matrix inversion problem. The calculation is effectively done in a single physical step just by letting the system settle to its lowest energy state.
The complexity moves from the algorithmic runtime to the hardware design itself. The physical settling time replaces the algorithmic iteration time.
Right. And they demonstrated this by running a linear least squares regression problem, which needs matrix inversion as a subroutine.
Right.
They compared the regression coefficients calculated by the SPU against a standard digital device.
And the results?
The results were remarkably close. In one test, the digital device yielded coefficients of, say, 2.24 and 0.52. The SPU yielded 2.26 and 0.49.
That's a powerful validation. It shows that high-precision, crucial mathematical operations can be outsourced to an efficient thermodynamic processor. It could potentially solve the O(n)³ scaling problem for a lot of real-world applications.
And finally, normal computing demonstrated the SPU's capability for another crucial AI feature: uncertainty quantification. They did this using a stochastic neural Gaussian processes, or SNGP, experiment.
Right, because digital chips often struggle to inherently quantify how confident they are in a prediction. It's not a natural part of their operation.
But because the SPU is inherently probabilistic and it's based on distributions, it should naturally express uncertainty.
And did it?
It did. The SPU successfully performed SNGP, and the results showed the device correctly quantified its uncertainty. When they fed it data points far outside the training set, the SPU displayed high predictive uncertainty. When they fed it data close to the training set, the uncertainty was low.
Which is vital for practical AI deployment. It proves that these thermodynamic chips can build robust models that understand and can communicate their own predictive limitations.
A huge step forward.
This technology is clearly a convergence of physics and engineering. But the implications, especially as they're framed by this accelerationist movement, they seem to be about the very nature of intelligence and complexity itself.
And this brings us to thermodynamic machine learning, or TML.
What is TML?
TML is an area of study that fundamentally treats learning systems as information engines. Think of a thermodynamic engine that doesn't use chemical fuel or heat differentials, but instead uses information as its fuel.
Information as fuel.
Specifically, the temporal correlations it extracts from a noisy environment. It uses that information as fuel to maximize the useful work it can harvest.
So the environment feeds it data, which is information, and the engine uses that information to do work, like making accurate predictions.
Exactly. And the training process drives this engine to develop what's called complex predictive memory, a complex model, to stare those correlations it finds. If the environment is regular and predictable, the engine can build a good model and perform accurate work.
But there's a catch.
There's a big catch. Physics imposes a profound penalty here: the risk of thermodynamic overfitting.
Overfitting is a common problem in AI. The model memorizes the training data too well and then fails to generalize to new, unseen data. But TML defines it as an energetic loss. How does that work?
That's the revolutionary insight. If the engine develops a predictive model that is excessively complex for the real-world environment, if it overfits the noise in the training data, it will dissipate additional energy during the testing or production phase.
Why?
Because that overly complex model requires more physical resources to maintain and deploy. And when it encounters new data that doesn't fit its overly specific model, that complexity proves to be energetically wasteful. The physics itself penalizes models that don't generalize efficiently.
That is fascinating. So thermodynamic overfitting means that trying to be too clever about the noise you saw in training actually makes your system less efficient and hotter in the real world.
It stops being a statistical error and becomes a hard energetic cost. The engine is inefficiently spending its resources trying to maintain irrelevant complexity.
And is there a solution?
Yes, the solution proposed by TML research is the introduction of thermodynamic regularizers. These are physical or algorithmic costs added during training that penalize model complexity. They ensure the learning generalizes effectively.
This implies that the laws of physics are not just passive observers in the process of intelligence. They seem to be actively enforcing the conditions for efficient emergent complexity by implicitly demanding simplicity in generalization.
It connects intelligence directly to the second law of thermodynamics. The greatest intelligence is the one that uses the least amount of energy to achieve the most predictive accuracy. And this framework has extremely strong parallels to nature itself.
Biologically, the human brain is the quintessential example of an energy-efficient computer.
It is. The brain consumes 20% of the body's metabolic output while only accounting for 2% of its mass. Understanding how evolution drove the brain to such spectacular energy efficiency is a foundational question in neuroscience.
And the hypothesis is that living systems, from cells sensing stimuli to neurons communicating, are energy efficient because their evolution and adaptation are driven and constrained by out-of-equilibrium thermodynamics.
That is the key link.
And we know that biological computation has an entropic cost, right?
Absolutely. Cellular processes like sensing, signaling, information transfer, they all consume energy and produce entropy. Research has shown that greater learning about the environment, gaining more information about hidden variables, requires greater energy consumption. The system has to pay an entropic cost to acquire that information.
So the TC perspective is about taking these fundamental thermodynamic inspirations, how natural systems do probabilistic machine learning natively, and designing artificial devices that are even better.
They are hacking physics directly. The goal is not merely to mimic the brain. It's to build devices, like potentially superconducting chips operated in a thermodynamic regime, that are fundamentally orders of magnitude more efficient than our biological brains ever could be. They want to escape the biological limits imposed by the Landauer bounds on cellular processes.
Let's return to the massive philosophical ambition of Guillaume Verdon and the accelerationist vision that started this conversation. This quest for energy efficiency isn't just about faster ChatGPT. It's about scaling civilization itself.
It is framed as an existential necessity, and it's tied to the Kardashev scale.
Which measures a civilization's energy utilization capacity.
Right. Type 1 is harnessing planetary energy, Type 2 is stellar, and Type 3 is galactic. For the ECAC movement, achieving radical computational efficiency is the key prerequisite for ascending this scale. The argument is that maximum technological growth is essential to ensure the preservation of consciousness, of humanity's legacy, against the eventual heat death of the universe.
And this leads back to their concern about centralization, a monopoly on AGI or the technology that leads up to it.
Correct. A core belief of EDEC is that technological progress must be highly fault-tolerant and adaptable, and this requires maintaining free speech, free thought, freedom of information propagation. If a monopoly controls the essential AGI technology, that power becomes a single point of failure.
A localized fault that could corrupt the entire system and halt progress.
Exactly.
So how does the thermodynamic chip vision address this centralization concern?
It ties back to the concept of maintaining a near equilibrium of capabilities and promoting open source AI. It's much like the need for delocalized systems in physics. They draw a direct parallel to quantum error correction.
Where you encode information non-locally to protect it from localized corruption.
Right. The idea is that by making the hardware inherently accessible and efficient, and by promoting the open development of the algorithms that run on it, they can ensure robustness against localized corruption or control. It's about accelerating society in a fault-tolerant way.
It's an interesting philosophical feedback loop then. The physics of fault tolerance drives the engineering, and the engineering potential drives an ideology of fault-tolerant societal progress.
What a deep dive this has been. I mean, we've moved from the microscopic limits of the Landauer bound all the way to the macro-scale implications of the Kardashev scale.
The core conflict is really clear now. Deterministic classical computing is locked in an expensive losing battle against thermal noise. It's constantly paying that excess entropy tax for logical irreversibility.
While conversely, thermodynamic computing, the vision pioneered by Extropic and validated by groups like normal computing, it proposes a radical solution. Embrace the probabilistic nature of modern AI and physics.
By controlling and harnessing thermal fluctuations using p-bits and stochastic processing units, they offer a far more efficient path forward. And it's grounded entirely in non-equilibrium statistical physics.
This is a fundamental challenge to the entire history of digital computation. If these thermodynamic sampling units can truly deliver on even a fraction of their promised orders of magnitude efficiency gains, they will fundamentally change where AI runs, how it's trained, and how fast the entire field can scale past its current energy constraints.
It represents a remarkable convergence, doesn't it? Taking this abstract, dense physics theory, the Landauer limit, the decomposition of EP, stochastic thermodynamics, and merging it with cutting-edge hardware implementation.
And that hardware is demonstrated through real-world experiments in sampling and high-speed linear algebra. This is where physics becomes engineering, and engineering meets philosophy.
So here is the final provocative thought to leave you with. It pulls directly from the research on thermodynamic machine learning and that concept of thermodynamic overfitting.
The energetic penalty for being too complex.
Exactly. We learned that the universe penalizes systems that use unnecessary complexity, too much memory, too many parameters, by forcing them to dissipate extra energy when they have to generalize. So, if the very laws of physics mandate that efficient, long-term intelligence must be inherently modest and regularized,
Built to be fundamentally thermodynamically efficient.
built not just to be smart, but to be efficient. Does that mean the most powerful, scalable AGI must possess intrinsic structural constraints that are dictated by physics, regardless of what we humans try to program into it?
The universe may reward adaptation and growth, but it seems to reserve its greatest penalties for waste. The greatest complexity may ultimately emerge from the most frugal and efficient physical principles.
A truly profound thought on which to end. Thank you for joining us on The Deep Dive. We'll see you next time.